Welcome to the Unit 5 Day 2 video. Go ahead, pause the video and work out this warm-up. There's a harder way and an easier way to solve this. Hopefully you find the easier way. When you're done, unpause and see how you did. So we need to solve for x and y. Three of these things have y. One of them has an x. One of them's got both x and y. So I'm going to try to avoid that one as much as I can to start with, meaning I can only solve with those two. Opposite angles in a parallelogram, which this thing is, are going to be congruent. So 6y minus 40 is equal to 4y. Okay, so that means that negative 40 is equal to negative 2y if I subtract 6y from both sides. Divide both sides by negative 2. You'll get that y is equal to positive 20. Now you have to use this in order to figure out what x is. You can plug it into any one that you want to. I'm going to plug it in there because that makes my life way easier. So 4 times 20 is 80. Now you can use this with any of these ones. Again, I'm going to try to avoid that if I can. I'm going to use the fact that this angle and this angle are going to be supplementary because they're same side consecutive interior ones. So I have 80 plus 2 times x plus 25 equals 180. Now I've got to be careful. I've got to distribute. So 80 plus 2x plus 50 equals 180. So 2x plus 130 equals 180. Subtract 130 from both sides. 2x equals 50. So x equals 25. Those are my two answers. Now, for this one, I want to make sure that I'm doing this right. Because if I plug in to here, 9 times 20 minus 2 times 25, which is what I just found, minus 30. I should get that that's the same thing as this angle over here. So when I find these values, that's 180 minus 50 minus 30, which is 100. Well, if I did this right and plug it in here, 25 plus 25 happens first. That's 50 times 2 is 100. Opposite angles are congruent. Awesome. Supplementary angles for being next to each other. Also awesome. So make sure that I did it right. That's one way we can check our answer. So in the last video, we talked about what a parallelogram is. Now we are going to talk about 3 special types. Okay? When I say types, these are special types. They have extra rules. So a rhombus, the plural, is either rhombuses or rhombi. I prefer rhombi. I think that one sounds more fun, but both are technically correct. This has 4 congruent sides. So it's a parallelogram that has 4 congruent sides. So the top and bottom are parallel, left and right are parallel, and this time we can say that all 4 sides are the same, so they get the same tick marks. A rectangle has 4 right angles. Pretty much everybody knows what a rectangle looks like. We still can only say that those ones are like that if they're all the same. So if I have 4 congruent sides and 4 right angles, then I have a square. Square is going to be your favorite. It gets the most special things. Now, remember, these are special types. There is just a generic parallelogram that does not have any of these features. That's just called a parallelogram. But these are special parallelograms. So we're going to talk about parallelogram corollaries, which it just means like extra special results from theorems. So a rhombus, the diagonals of a rhombus are perpendicular bisectors of each other. A rectangle, the diagonals are congruent. And squares, all of the above, the diagonals are perpendicular bisectors of each other and are congruent. Squares just extra special things. It's a rhombus and a rectangle all at once. So if we're going to fill out this Venn diagram, okay, if I say I've got this left circle is 4 congruent sides, this right side is 4 right angles. In the left circle I would have a rhombus and a square, but a square is also inside the 4 right angles. So it would look like this. Now, if I want to be super technical, I'm going to actually have another giant circle encompassing all of these that just says these are types of parallelograms. And inside this circle, but outside the other Venn diagram, is just parallelogram. A generic parallelogram that does not have 4 congruent sides, does not have 4 right angles. So that's one way you can visualize all of these different rules. Now, a few of these theorems. A parallelogram is a rhombus if and only if the diagonals are perpendicular bisectors. What that means is the if and only if. I think this is probably the first time you've ever heard that. If I say this is a parallelogram, you know automatically the diagonals are perpendicular bisectors. If during a problem you know this is a parallelogram but you don't know what kind, but you're able to see that the diagonals are perpendicular bisectors, then you automatically know it's a rhombus. That's what if and only if means. You can read it either direction and it'll still be true. So parallelogram is also, it's got another one. It's a rhombus if and only if the diagonals are angle bisectors. So let's draw this out and kind of see what's happening. So with our diagonals, we know based off of the notes from last time that they are segment bisectors of each other. So we get that for free. Now we also have some extra special information. Because this is a rhombus, we also know all of these sides are the same. So if you look at the 4 small triangles, they all have 1 mark, 2 marks, and 3 marks. So all 4 of these triangles are congruent. They're corresponding parts. They all meet at this point, so they all have this angle corresponding. And if they're all going to be congruent, they have to be 90 degrees. So that tells me that I've got perpendicular, and then we already knew they were bisectors, so the diagonals are perpendicular bisectors. That's awesome. The other part is that diagonals are going to be angle bisectors. Well, if I just look at, I'm going to look at these 2 triangles right there to make this point. This side's the same, that side's the same, this angle, that angle. This angle is going to be the same, that angle is going to be the same. Which means that these angles have to be the same. Since they're the same, this diagonal is cutting it right in half. Diagonals are angle bisectors because it's going to be the same thing all the way around that triangle for that exact same reason. Just pick a different set of 2 triangles that are sharing that one side. Next one is about rectangles. A parallelogram is a rectangle if and only if the diagonals are congruent. We've already mentioned this one. All right, so if the diagonals are congruent, if we draw this out, we're going to hopefully see. I did a better job drawing this time. Good. We already knew that they bisected each other, but if they are the same length and they bisect each other, each of these 4 pieces is going to be the same. That's what we get from this theorem. Okay, it's awesome that the diagonals are congruent, but we really more so care about the fact that those 4 pieces of those diagonals are all congruent. And now we've got the mother of all proofs. 13 steps. It's a lot. Very much is a lot. But most of these steps are very, very basic. And by basic, I mean there's going to be like add subtract, reflexive, things like that. Things that are pretty simple to do. So the first thing we have to do in this proof is write what we're given. ABCD is a rhombus. So we know based off of our theorems that these diagonals are perpendicular to each other, but that's what we're asked to prove. Since we're asked to prove that, we're not going to use that theorem. All right? That's why it's 13 steps. If we were not proving that theorem and it was just like, hey, is this true? You could prove it in one step. All right? We're going to have to do a little bit more. So first thing we're going to do, since we're given that it's a rhombus, we're going to use the definition of a rhombus. Definition of a rhombus is we've got 4 congruent sides. So it tells me that AB is congruent to BC, is congruent to CD, is congruent to DA, or AD. All 4 of those sides are the same. But now, like I've said in the past, our goal is basically prove 2 triangles are congruent. So I'm going to pick 2 triangles. I'm going to pick these 2 triangles up here. So I'm going to ignore all of this stuff down here for right now. I picked those 2 triangles kind of arbitrarily. It doesn't matter which 2 you pick, but what you're going to want to do is pick 2 triangles that are adjacent to each other, that share this side. If we pick across from each other like we did in the last set of notes, it's not going to help us figure out that these are perpendicular. All right. So step 3, my goal is to try to prove those 2 triangles are congruent. Well, I've got a couple things I can do. First off, I could say that BE is congruent to BE by the reflexive property. That one's pretty easy. So I've got 2 sets of sides. I almost said step 3 again. Step 4. This was a rhombus, which is a type of parallelogram, and we know that diagonals of a parallelogram bisect each other, right? So that means that segment BD bisects segment AC. So segment AE is congruent to segment EC by the definition of a segment bisector. Right? Or you could write diagonals of a parallelogram bisect each other, so diagonals of a rhombus bisect each other. That would be perfectly fine as well. I should have marked that with 3 tick marks. So now I've got 3 sets of sides. So triangle ABE is congruent to triangle CBE by side, side, side congruence. So step 6 is Cpctc. Now the part that I care about, I'm wanting to show that these diagonals are perpendicular. That's my goal. Well, that means I need to know stuff about these angles at where the diagonals intersect each other. So the angles I care about are those ones. So I'm going to say that angle AEB is congruent to angle BEC by Cpctc. It's not enough to stop right here. So we show that they're congruent, which is awesome. But what we're going to have to do is show that they also add up to 180 degrees. All right? So step 7 and step 8, you can flip-flop. Doesn't really matter which one you do first. I'm going to say that the measurement of angle AEB plus the measurement of angle BEC equals 180 degrees. That's our linear pair postulate from way back when. Okay, if you've got 2 adjacent angles that form a straight line, they are a linear pair, they add up to 180 degrees. So step 8, since I'm wanting to use things about the measurement, I have to go back from step 6 and say the measurement of angle AEB equals the measurement of angle BEC, and that is just the definition of congruent. So that's one we've used I don't even know how many times. Now, step 9, we know that one of these equals the other. I'm just going to replace in step 7 one of them. Does not matter which one, you just don't want to do both. I'm going to say measurement of angle AEB plus measurement of angle AEB equals 180, and that was by substituting. I replaced the value of measurement of angle BEC with the measurement of angle AEB because they're the same, and now it's just an algebra problem. When you have a like x plus x equals 180, your next step would be 2x equals 180, so 2 times the measurement of angle AEB equals 180. By simplifying, we combined like terms. Now we're going to divide both sides by 2. So our reasoning is we just divide it. So if we've got the measurement of an angle is 90 degrees, that means that it's a right angle. So angle AEB is a right angle by the definition of a right angle. And finally, we can say that segment AC is perpendicular to segment BD by the definition of perpendicular. Okay, if two things are perpendicular, that means they meet to form right angles. We just showed that they make right angles because we got that this is a right angle and it's the same as this other angle, which is a right angle. So there we go. 13 steps. But like I said, most of these are pretty simple. Definition of rhombus is brand new today. Reflexive we've used a bunch. Definition of segment bisector has been around for a while. Same with SSS and CPCTC and linear pair postulate. The definition of congruent, substitute, simplify, divide. These steps individually are not very complicated. Collectively, it makes it a lot harder because you have to piece a lot of pieces together. I understand that. Okay, but this is the process to be able to prove this. Now we can just say it all the time. We're good to go. So again, I already wrote down all the way past where it says what your homework is. It will be a good idea to write down questions you might have so you can ask them when we have class or send me an email or something. Otherwise, I hope everybody has a great day and you work through this homework and that it goes well for you. Have a good one.